Hey guys, Mr. McKinney here, just doing a quick review of AP's Unit 5, which is Analytical Applications of Differentiation. This is probably the biggest unit we've done so far. It covers a lot of theorems and we get into some pretty difficult word problems towards the end. We also look at the relationship between f, f prime, and f double prime, which will help answer a lot of different types of questions on the AP exam. Let's start with the mean value theorem. So when we use the mean value theorem, we need to keep in mind that the function must be continuous on the closed interval, differentiable on the open interval. If it is continuous on the closed and differentiable on the open, then there's at least one point on that open interval where the slope at that point, so the value of the derivative at that point, is equal to the slope going through the two endpoints. So at some point, the slope of the tangent line is equal to the slope of the secant line if it's continuous on the closed interval and differentiable on the open interval. Let's look at some examples. So why don't you guys try this one? So hit pause and see if you can figure out first if it satisfies the conditions, and if it does, what is the value of C? All right, let's see how you did. So you would start by taking the derivative so that you can see if it is continuous and differentiable. So the derivative here would be 2x minus 4. So I want to know, is it continuous on the closed interval, and is it differentiable on, the open interval? So for continuous, look at the original function. Is there any place where you're dividing by 0 or taking the square root of a negative? Is there any place where it's undefined? Nope, polynomials, we're all good, so it is continuous. For differentiable, you do the same thing with the derivative. So you look for where the derivative would be dividing by 0, or where the derivative would be taking the even root of a negative, not just a square root, an even root of a negative. But 2x minus 4, that has a domain of all real numbers. So from 3 to 4, it is differentiable as well. If both of these things are true, then you're going to want to find the slope going through the endpoints, and the slope equation, which is the derivative, so this will tell you the slope at any given point. So you'll set 2 f prime of c would be 2c minus 4. So 2c minus 4 equals whatever the slope is going through the endpoints. So x2 minus x1 is going to be 4 minus 3, and f of 4 minus f of 3. So you guys can do that on your own. Plug in 4, plug in 3, simplify that, and then solve for c. I've got it worked out. So when c is 7/2, which is on this interval, so when c is 3.5, the slope of this function would be the same as the slope going through the endpoints. Here's another example. So we'll go ahead and figure out if it satisfies the conditions of MVT, and if it does, find the value of c. Go ahead and hit pause and give it a shot. All right, let's see how you did. Hopefully you guys didn't spend too much, because you don't have to work this one all the way out. Again, I'm going to be looking at the derivative. So the derivative would be 4/5 x to the negative 1/5. Derivative of 5 goes away. This could also be written as 4 over 5 times the the fifth root of x. So we want to know if it's continuous on the closed interval from -3 to 4, and we want to know if it's differentiable on the open interval from -3 to 4. So to figure out if it's continuous, we look at the original function. Is there any point where I'm dividing by 0 or taking an even root of a negative number? We're taking an odd root, so that we're fine. You can take odd roots of negative numbers, and we're not dividing by anything here, so we're not dividing by 0. So we are continuous. Now when I look at the derivative, I can write it like this. If x is 0, I would be dividing by 0, and 0 is on this interval, so it is not differentiable. So at this point I can stop. There may be a point where the slope is equal to the slope of the secant, but we don't know for sure, so we can stop. If you think about what this graph would have looked like, so x to the 1/5, a fifth root function looks a lot like a cube root function, something like that. And then if I were to take that to the fourth power, it would multiply everything times itself 4 times, so anything that was negative would come in and become positive. It's differentiable everywhere except right there. All right, moving on. The extreme value theorem, this is the one that I think is the easiest. If f is continuous on a closed interval, then it has a maximum and a minimum. Keep in mind that a and b must both be finite, and it has to be a closed interval, not an open interval. Basically, if the two endpoints are connected, you have to have a highest point and you have to have a lowest point. And you guys will see how this is asked on the AP as you work through the practice. All right, let's get into some more theorems. So in order to figure out if a function is increasing or decreasing, you're going to want to look at the first derivative. So if the first derivative is positive, then the original function is increasing. If the first derivative is negative, then the original function is decreasing. So if you want to know if something is increasing or decreasing, you're asking if the rate is positive or the rate is negative, and to find the rate, you're going to look at the derivative. If you're looking for local extremes, the only place that that can happen is if the derivative is equal to 0 or the derivative is undefined. We call these points critical points. So the max or the min would happen at a critical point. Not all critical points are going to be a max or a min because you might just flatten out and then keep going up. You're going to look for a sign change, but any local max or local min will happen at a critical point. The max or the min is either going to be at the top of a hill or at the top of a cusp or at the bottom of one of those things. All right, so if a question asks you to find the extremes of a function, you're going to want to look at the derivative, and then usually a sign table will help you find the extremes. So why don't you hit pause and give this one a shot. All right, let's see how we did. So you'd want to take the derivative, f prime of x. I always write this as cosine of x squared, so I don't forget to do the chain rule. So 2 times cosine of x to the first power, and then the derivative of cosine is negative sine of x. Derivative of negative cosine would turn into positive sine of x. You can factor out the sign if you want. You don't have to. And this one's all worked out on the next slide. So when x is pi over 3, your derivative would be 0. When x is pi, the derivative would be 0. And then when x is 5 pi over 3, the derivative would be 0. In order to figure out if it's a max or a min, not only does the derivative have to be 0 or undefined, but you need to check the value of the derivative on both sides. If it goes negative to positive, then we are at a minimum. Maybe an absolute, but definitely a local. Because we were decreasing, and then we flattened out, and then we were increasing. So we went down and then went up. This can be 0 or undefined, because it could look like that also. So that'll tell you a local min. If you go from positive to negative, that's going to tell you a local max, and then again, negative to positive is going to be a local min. Now, these sign tables will help you figure out whether it's a local max or a local min, but you're going to need to use words when you're explaining your answer. So you would say there is a local max when x equals pi at 2. And keep in mind that the max is 2. The max is not pi, and the max is not the point necessarily. The max is the y value. So you'd say the max is 2, and you can tell it's a local max because the derivative changed from positive to negative. All right. The second derivative will help you figure out concavity. So a function will be concave up if the second derivative is positive. So when the rate of change is positive, or when the slope is increasing, these are all ways of saying the same thing. Function is concave down when the slope is decreasing. So the slope is getting less, or the rate of change is negative. The rate of change is decreasing, which means that the rate of change is negative, or the second derivative is less than 0. It's easy to remember what they look like. Concave up, just take the C and up, concave up. Concave down, remember that it looks like a frown. So concave up looks like a cup, concave down looks like a frown. If the original function is concave down, the second derivative is negative. If the original function is concave up, the second derivative is positive. Where a point, or the point where a tangent exists, where you switch concavity, is called a point of inflection. So if the second derivative is 0 or undefined and it switches from either positive to negative or negative to positive, you've got a point of inflection. So if you switch from being concave up to concave down, that's called a point of inflection. All right, so this question asked me to find the extrema and the POIs. So find the maxes and mins, local and absolute, and find the points of inflection. All right, this first problem we don't have any on this problem we don't have any endpoints. So when I look at the derivatives, I'm not going to have endpoints to check, but I do need to be thinking about the end behavior when I'm looking for the absolute max and min. All right, go ahead and hit pause and give it a shot. All right, let's see how we did. So we take the first derivative and the second derivative, set them equal to 0. So there's my first derivative, there's my second derivative. In order to set them equal to 0, I'm probably going to want to factor it. So the first derivative would be 0 when x is 2 or negative 2. Second derivative would be 0 when x is 0. So we're going to fill in our table and then check positive or negative on each side. Here we go. So the first derivative changed from positive to negative here, which means that's a local or relative max. The relative max would be 11. The second derivative changes from negative to positive, so that's a point of inflection. And then down here we've got a first derivative going from negative to positive again, so that would be a relative minimum. So relative max if the first derivative goes positive to negative, relative min if the first derivative goes negative to positive, and then the second derivative will show you where a point of inflection is. Whether you go negative to positive or positive to negative, it would be a point of inflection. Now these tell me the relative max or min. To find the absolute max or min, I would look at the endpoints. Since I don't have endpoints, I need to think about what's happening. So before x is negative 2, I am increasing. So I'm starting with an increasing function, which means that this arrow is going down forever on the left side. So there is no absolute minimum. And then something happens in here. Basically, I flatten out and I decrease. And then I flatten out again and I start increasing. Now this increasing over here past 2 tells me that I'm going to positive infinity. Since I'm going to negative infinity and I'm going to positive infinity, there are no absolute max or min on this problem. So here's the summary right there. And this chart I would write down over and over again until you know it like the back of your hand, which is a weird saying. But if you're looking for extrema, if you're looking for maxes or mins, the first derivative is either 0 or undefined. Any place where that happens is called a critical point. I like to think of these as possible extrema, because you could just have a stationary point where the derivative is 0, but it doesn't switch from increasing to decreasing. So right here, you might have a horizontal tangent line, but it's not a max or a min because we keep going up the whole time. So look for that sign change. If you don't talk about the sign change on the AP exam, you'll miss it. For concavity, you're going to look at the second derivative. It's going to be either 0 or undefined. The points where the second derivative is 0 or undefined are possible points of inflection. If you actually have a sign change in the second derivative, that's when it's an actual point of inflection. All right, and that's where we're going to wrap it up for this first video. Hope it helped.